Let's take a look at what happens when air becomes saturated. First of all, again, it means that relative humidity is approaching 100%. The air is holding as much water vapor as it possibly can. And once it becomes saturated, you're going to have condensation or deposition form in the atmosphere. And typically this means cloud formation. And clouds, as we'll talk more about in the next chapter, are liquid and/or ice particles. So they're made up of tiny little cloud droplets that are just little bits of atmospheric stuff, little particulates that provide surfaces for water vapor to condense onto. Humidity increases when air is cooled. And again, that's because warm air can hold more moisture than cold air. So if you cool air, suddenly the air can't hold as much moisture, and so the humidity level, the relative humidity, if you want to think of it that way, increases. Humidity also increases if you add water vapor to the atmosphere and hold the temperature constant. So as an ascending saturated air parcel whose relative humidity is close to 100%, expands and cools to the dew point temperature, condensation occurs in the atmosphere. So remember we talked about the dry adiabatic lapse rate in Chapter 5. The dry adiabatic lapse rate describes the temperature cooling profile of dry air. So if we start off with an air parcel that's forced to rise for some reason, it's going to expand as it rises because it encounters less atmospheric pressure the higher up it goes in the atmosphere. And expansion is a cooling process. And the cooling rate was about 10 degrees Celsius, minus 10 degrees Celsius per kilometer, per 1,000 meters. And then if the parcel goes up another 1,000 meters, it expands even more and cools off even more at the same dry adiabatic lapse rate of negative 10 degrees Celsius per 1,000 meters. And then if the air parcel has to fall back down, it compresses and warms at the same rate. So these adiabatic processes are important for talking about what happens to air as it rises and cools. So air cools as it rises, again because lower pressure higher up in the atmosphere allows the air to expand. And we talked about the unsaturated or the dry adiabatic lapse rate that air cools at. There's that negative 10 degrees per 1,000 meters, which is also 5.5 degrees Fahrenheit per 1,000 feet. And then it warms at the same rate upon descent. Upon saturation, air will continue to cool, but it switches from the dry adiabatic lapse rate to the moist adiabatic lapse rate, which is not quite as extreme. It's minus 6 degrees Celsius per 1,000 meters, or minus 3.3 degrees Fahrenheit per 1,000 feet. And remember, this changes depending on how much moisture is in the atmosphere. So we're building up to talk about atmospheric stability. And stability in the atmosphere just describes the state of warm air and cold air as we look vertically in the atmosphere. So if we're at the surface here, if we have cold air at the surface and warm air aloft, we have a stable environment. The cold air is happy to stay where it is. Cold air wants to sink, warm air wants to rise, and so there's no tendency for vertical movement here. This is stable, a stable atmosphere. On the other hand, when we end up with warm air underneath cold air, that warm air wants to rise and the cold air wants to sink, and so there is a tendency for vertical movement here. And that tendency for vertical movement makes it an unstable atmosphere. So how do we determine atmospheric stability? Well, we have to compare the temperature of some air parcel that's forced to rise to that of the surrounding air. So the surrounding air temperature profile is collected via soundings. And we saw in a previous chapter the radio signs that go up on the weather balloons and one of the weather variables they collect is air temperature. Once we get that profile of how the actual air temperature is behaving as it goes higher into the atmosphere, we get what's called the environmental lapse rate. So that's the actual change in temperature as we go higher up into the atmosphere that's based on this direct observation, these soundings. So once we have this information, then we can compare what happens to a parcel of air that starts off at the surface of the Earth if it were forced to rise. So if the rising air is colder than its environment, it will be more dense and wants to sink back down to Earth. It doesn't want to rise, in other words. So we know that it's a stable environment. On the other hand, if the rising air is warmer than the surrounding air, it wants to keep rising. And it will keep doing so until it reaches the same temperature, until its temperature is the same as the environmental temperature. And we call this unstable air. So we can look at this by charting it out with these charts that you see here. So the first one shows stable air, and what we're comparing here is the environmental lapse rate. Again, this is the lapse rate or the temperature profile that's obtained through soundings, and we're comparing that to the dry adiabatic lapse rate, which is a constant -10 degrees Celsius per 1,000 meters. So in this example, the environmental lapse rate is -4 degrees Celsius per 1,000 meters. So it's cooling more slowly than the dry adiabatic lapse rate. So we have temperature across the x-axis and height or altitude above or on the y-axis. Over here, we have a parcel of air. It starts off at the surface at the same temperature as the surface was found to be. And this little helicopter is just showing that we're forcing this parcel to rise. So you can imagine a little bitty helicopter driven by little bitty fairy people that's pulling up these little bitty air parcels. So we're assuming here that this air parcel is going to cool at the dry adiabatic lapse rate. So if it starts at 30 degrees and it's forced to rise up 1,000 meters, it cools off at the dry adiabatic lapse rate of -10 degrees per 1,000 meters, so it cools down to 20 degrees Celsius. When we compare that to the surrounding air temperature, the actual air temperature, we see that that air parcel is colder than the actual air. So we have what's called a stable environment. If we continue to force this parcel to rise, the little helicopter's pulling it up higher in the atmosphere, it goes up another 1,000 meters and cools off another 10 degrees Celsius. We're down to 10 degrees now. Compared to the environmental lapse rate temperature of 22 degrees, we're still colder than the surrounding air. So we do not want to rise, we want to sink. And then finally, if we go up another 1,000 meters, we cool off another 10 degrees Celsius. And when we compare that to the environmental lapse rate, we see that the surrounding air at this height is 18 degrees Celsius. We're still colder. So this is indicative of a stable atmosphere. So you notice here that the environmental lapse rate is decreasing at a slower rate than the dry adiabatic lapse rate. So in other words, the environmental lapse rate is over here to the right of the dry adiabatic lapse rate, and that is stable air. Let's take a look at unstable air now. Same deal. We have our dry adiabatic lapse rate at its constant of -10 degrees Celsius per 1,000 meters. This time our environmental lapse rate was found to be -11 degrees Celsius per 1,000 meters, and it's plotted here in the gray line. So we've got our parcel of air that starts off at the temperature of the surface at 30 degrees Celsius, and then the actual air temperature, these values are coming from the environmental lapse rate, so it's changing by 11 degrees Celsius per 1,000 meters, but our parcel of air here is lifting and cooling at the dry adiabatic lapse rate. So at the surface we're the same, but if that parcel of air is forced to rise up 1,000 meters, it has cooled to 20 degrees. Compared to the surrounding atmosphere, whose temperature is 19 degrees, we're warmer. So this parcel of air wants to continue to rise. And if we force it to rise up another 1,000 meters, it cools another 10 degrees compared to the surrounding environmental temperature, the ambient air temperature, which is 8 degrees. We're still warmer, so we still want to rise. So this is unstable, right? When the parcel of air is actually warmer than the surrounding air, that's an unstable environment. And if we increase or raise that air parcel up another 1,000 meters, it cools by another 10 degrees Celsius to 0 degrees compared to the ambient air temperature of 3 degrees. Now it's colder, so it wants to sink down somewhere to, where these two would be the same. So somewhere in between these two guys. So this is unstable air. So our environmental lapse rate is changing at a faster rate than the dry adiabatic lapse rate. And you can see that that line is over here to the left of the dry adiabatic lapse rate, and that shows an unstable atmosphere. Another status of stability is something called conditionally stable, or conditional stability. And this occurs when you compare what's going on with this parcel of air to the environmental lapse rate, as we've been doing, and you also compare it to the dry adiabatic lapse rate, and then also to the moist adiabatic lapse rate. And you find that it falls somewhere in between. So in this example, the dry adiabatic lapse rate is its constant, negative 10 degrees Celsius per 1,000 meters. Here, the environmental lapse rate was found to be negative 7 degrees Celsius per 1,000 meters. And we can look at what happens to our air parcel as we force it to rise and compare it to the surrounding temperature. So they start off the same at the surface. As the air parcel is forced to rise 1,000 meters, it's cooled down to 20 degrees Celsius, which is cooler than the surrounding air. If we force it to rise another 1,000 meters, it cools off to 10 degrees Celsius, still cooler than the surrounding air. And if we force it to rise up another 1,000 meters, it's cooled to 0 degrees Celsius, still cooler than the surrounding air. So this is stable with respect to the dry adiabatic lapse rate. Now, if we take a look at the temperature of this air parcel, if it is cooled at the saturated air or moist air lapse rate, then we see here the moist adiabatic lapse rate is negative 6 degrees per 1,000 meters, and the environmental lapse rate is the same as it was over on that side, so negative 7 degrees Celsius per 1,000 meters. They start off the same. As we force that air parcel to rise, it cools off at the moist adiabatic lapse rate this time of negative 6, so it cools off by 6 degrees, which is warmer than the surrounding air, so it wants to rise. If we force it to rise to another 1,000 meters, it cools another 6 degrees to 18 degrees compared to 16 degrees of the surrounding ambient air. Warmer, it wants to rise, so unstable. If we go up another 1,000 meters, it cools another 6 degrees to 12 degrees compared to the ambient air, which is 9 degrees, still warmer, it wants to rise. So this is the case where it's stable when we compare it to the dry adiabatic lapse rate, and unstable when we compare it to the moist adiabatic lapse rate. So we call this condition conditionally stable. So how do we know? Stable or unstable? What's going on? So here's a graph that shows the dry adiabatic lapse rate in red and the moist adiabatic rate in blue. And where our environmental lapse rate falls will tell us. If it's somewhere over in this area, then it's absolutely unstable. So, whoops. So if it falls over somewhere on this side, it's an absolutely stable atmosphere. So if this is our environmental lapse rate, over on this side, we have an absolutely stable atmosphere. If the environmental lapse rate falls between the two, then we have a conditionally unstable atmosphere. And if the environmental lapse rate falls over on this side in the pink zone, we have an absolutely unstable atmosphere. So this graph even charts it out further. So here's the dry adiabatic lapse rate. Here's the dry adiabatic lapse rate. Here's the moist adiabatic lapse rate. And where we are decides what type of situation we have. If we're over here on the pink side, this is stable. If we're down here on the blue side, this is unstable. And if we're somewhere in the middle, this is conditionally stable. But I want to point your attention here to the stability side. We have 3 different classifications of stability. So there's just regular old stable, which we call lapse. The category is lapse, and that's C. So that's when the temperature of the environmental lapse rate is cooler above than below. So it's cooling as we go up in the atmosphere. D, which shows a line that's vertical, is when there's no change in the temperature from the surface up to the higher levels of the atmosphere. We call this an isothermal situation. So the lapse rate is a constant here. So the lapse rate shows no change in temperature. And then finally, we have an inversion occur when it actually gets warmer higher up in the atmosphere than at the surface. So you can see it's warmer higher up than it is lower. So let's talk about these different conditions here with the definitions written out for you. Absolute instability is when the air temperature is dropping more rapidly with altitude than the dry adiabatic lapse rate. So the dry adiabatic lapse rate, 9.8 or 10 degrees Celsius, so negative 10 degrees Celsius per 1,000 meters. So if the air temperature is dropping quicker than that, we have unstable atmosphere. Conditional instability is when the air temperature is dropping with altitude more rapidly than the moist adiabatic lapse rate, but less rapidly than the dry adiabatic lapse rate. So it's right in between the two. The air layer is stable for unsaturated air parcels and unstable for saturated air parcels. This implies that unsaturated air must be forced upwards in order to reach saturation. Absolute stability is when you have an air layer that's stable for unsaturated and saturated air parcels. Another way to say that is the environmental lapse rate drops more slowly with altitude than the moist adiabatic lapse rate. Temperature does not change with altitude. We call that situation isothermal. And if temperature increases with altitude, we call that an inversion. And then a neutral air layer is if rising or descending air parcel has the same temperature as ambient air. So it neither impedes nor spurs up or down motion of air parcels. We call it neutral. This schematic shows a temperature inversion. You've maybe heard of temperature inversions. Typically, what's a normal situation is we have warmer air closest to the Earth's surface, and then it cools as you rise in the atmosphere. And that allows all the heat that builds up over the day, especially in an urban environment, to dissipate and cool off at night. When we have an inversion layer occur, remember, an inversion is when you have warm air on top of cold air, and then there's usually some cold air higher aloft, higher up in the higher levels of the atmosphere as we get into the top of the troposphere. But with an inversion, this layer of warm air acts like a cap on the movement of air down here. So it's cold down here. Any heat that wants to rise up can do so, but then it reaches this warm layer and it sinks back down. It can't get past this layer. So what happens is if there's any pollutants in the atmosphere, if there's any smokestacks or people are burning chimneys in the winter, or there's just a lot of sand and debris in the atmosphere, it gets trapped by this inversion layer, and the area can become very polluted if that inversion layer persists for long periods of time. Stability can change, and it can change through these different things, these different methods you see here. One is through local radiational heating and cooling. At night, the ground cools off and it stabilizes the overlying air. As that warm air rises and cools, it causes a stable condition. During the day, when the ground warms, that warm air close to the ground wants to rise, and that destabilizes the overlying air. So there's that factor. There's also air mass advection. The air mass is stabilized as it moves over a colder surface. So the cold air is happy to stay down low where it is, and warmer air can lay on top of it. And if the air mass is destabilized, that will happen as that air moves over a warmer surface, and that warm air wants to rise up. When you have that tendency for vertical motion is when you have instability. And then finally, we have large-scale ascent or descent of air. So subsiding or sinking air is generally more stable than rising air, which is the definition of instability. A Stuve diagram is a way to chart out the amount of humidity and the temperature profile of air as you move higher up into the atmosphere. You can see it's a fairly complex graph. It's showing temperature, altitude, pressure, and then it's also showing the amounts of water vapor in the atmosphere. And here we have the dry adiabatic lapse rates, so the different adiabats, and the moist adiabatic lapse rates in the green dashed lines. So it's a very complicated graph, but what happens is you can send a sounding up into the atmosphere and get actual air temperatures and plot them on this graph and see what's going on and be able to determine stability and instability at different levels of the atmosphere. So let's take a look now at how air can be forced to rise. We don't really have little tiny helicopters that force our air to rise. Although, I'm not saying that can't happen. It's not really been proven to occur. So what has been proven to occur are these processes, beginning with convection, which we spoke about in Chapter 3. So convection, remember, is when the ground warms up. Convection are big drafts or currents that move through liquid. In this case, the atmosphere is a liquid. So the ground warms up and rises, and we get these currents, these convective currents. And when air is forced to rise through this current, any moisture that's in that air may reach its dew point temperature, at which clouds will develop. We see these cumulus clouds develop in this case. And then on the other side of this large current, we have a downdraft, which is not promoting cloud development. In fact, it won't allow clouds to develop. So we see parts of the sky where there are clouds, and then parts that are cloud-free where the air descends. So this is one way of forcing air to rise. Another way is through frontal uplifting. So this is when air masses meet and we have frontal boundaries. So there's a couple of things going on here. Here's a cold front. We'll talk about fronts later in this course, but here's a cold front, so a big mass of cold air moving in where warm air existed, and that warm air is forced to rise up over that cold air. And so we get cloud development and often storms in front of a cold front. And then here's a warm front that's moving in where cold air existed. And again, that warm air wants to rise up over the cold air, and as it does, we have that potential for cloud growth. Another way that air is forced to rise is through orographic uplift, which refers to the topography of the Earth having an impact on how the air moves. So airflow moves along the surface of the Earth, and when it encounters mountains or some high point, that air is forced upwards. And as it's forced upwards, again, it cools. And if it cools to the dew point temperature, clouds will form. And if those clouds become large and developed enough, they can precipitate. They can cause moisture to fall. So what we see a lot with orographic uplift, with mountain ranges, is we have a windward slope. So the wind is coming from this direction, and it encounters the mountains and is forced to rise. The clouds develop and it rains on the same side of this mountain. And then on the other side, there's no more moisture as the wind has, gone through this pattern of rising up, causing the clouds, and then finally moving on over here. There's no more moisture left. So we end up with a wet side of the slope and a dry side of the slope. Here's an example of that. This graph or this picture shows the mean annual precipitation in the Pacific Northwest in centimeters. You can see the scale across the bottom here. And there's a mountain range here, the Cascade Mountains, and the coast range here. So air flows in this direction off the Pacific Ocean from west to east, and as it encounters these mountains, it's forced to rise, and as it rises, it causes cloud development and thunderstorms, precipitation events to occur. And you can see that this western side of the mountain range has much higher precipitation amounts than this drier leeward side of the mountain. So all the precipitation falls on the windward side of the mountain, and on the other side it's very dry. Another way to force air to rise is through convergent lifting, convergent uplift. This is when surface winds converge and move upwards. We saw in a previous chapter, if you have low pressure, it causes winds to want to move in. Air wants to move into areas of low pressure, and we have this convergent motion. And once it converges, it has nowhere to go but up. So as it rises, we have cooling air parcels that can cause cloud development and, in fact, thunderstorm development with these low pressure systems. The same dynamics are in play in the peninsula of Florida. Tampa, in case you didn't know, is the lightning capital of the world, and for good reason. Florida is a peninsula, and we have sea breezes blowing from both sides, and these wind barbs are showing the direction of the wind. They always point in the direction the wind is blowing. So the wind is blowing in this direction from the west to the east on the western side of the peninsula, and over on the eastern side of the peninsula on the Atlantic coast, the same thing's happening. We have a sea breeze going on, so the winds are blowing off of the sea onto land. Well, this is a relatively narrow strip of land here, so these two processes cause convergence of wind in the peninsula, and where the wind converges, it's forced to uprise, to lift up in the atmosphere. Clouds develop and thunderstorms occur, and you can see in this image thunderstorms that are developing on the peninsula. Okay, that's the end of this lesson.